3 Mondays, Ale. So our first speaker is Boris Baeumer from the University of Otago. Welcome, Boris, please. Well, yes, the title, Intermittent Nonlinear System with Noise and Derivation from First Principle.
Thank you very much, Vasily. And thanks for the opportunity to give a talk at this nice venue. I would have loved to be there, but maybe some other time. Just happened to yesterday talk to my parents, and thank goodness I did, because yesterday the slides still read 11 p.m. because you have a time change and we change our time in a week from now. I almost would have missed that little detail and would have been an hour late to my own talk. But anyway, so today I want to talk about how to derive intermittent nonlinear systems with noise from the very beginning. And it seems that seeing some of the talks at our workshops and so on, that it might be interesting to some to see, you know, how to go there from a probabilistic point of view, and how you can build things up where you actually have a solid foundation, rather than throw an alpha derivative onto something and hope that it models something. All right, so a good place to start is usually a random walk. It's a very basic model. Where's the drunken sailor? Yeah, so as assumption, he or she stumbles through the night, and he doesn't care where he or she is. So we have stationary increments, doesn't care what time it is. So it's autonomous, time independent, and doesn't really care whether there are other sailors around. In that sense, it is not densely dependent and is a linear probabilistic walk. Okay, so mathematically, it's drawing from the same probability distribution J to travel some vector x in a specified time interval, delta t. Okay. So the question that we want to answer is, where is he at the end of the night? Okay. And here one of the answers is that if we can let delta t go to 0, so if we do have a chance of writing this in terms of differential equations, so that any big tumble is made out of little stumbles, so that things are what is called infinitely divisible, then there's a famous Levi-Kinshin formula says that the only way that this can be done is if your location P, the Fourier transform of it, is given by this formula right here. There's slight variations in this formula, whether there's a 1 plus mod x squared on indicator function or so on. But in all of those formulations, it is always that the velocity vector is unique, the covariance matrix Q is unique, and the Levi measure phi is unique, and giving you the jump distribution of or the non-locality of your potentially of your random walk. Okay, so if you have that, okay, then you usually can get to differential equations, and there are usually 2 or 3. One is Feller equation, or sometimes also a backwards equation, where you get a solution as the expectation of some function f of p of t. Okay, so you will solve this red differential equation, and it has a generator where the generator, the domain is given by all continuous functions whose vector operator A is also a continuous function applied to it. And then we say that AG is equal to H. And then you have the whole machine of the semigroup theory to give you the evolution of U. Okay. The nice thing about the Feller equation is that this always exists when you have a nice Markov process. Okay. The Fokker-Planck equation is something that usually physicists are more interested in. That is something where you start with a probability distribution, and then the solution to your differential equation gives you the evolution of the probability density of where it can be, or concentration, or whatever you model. Whatever you're modeling. Yeah, and so here now the dual of A star is then now an element that's usually in the space of measures, but you restrict yourself to the space of L1 would be the natural space to restrict yourself to that, so that you can still get nice strongly continuous semigroups, and the other domain is then all the functions H and L1 for which the Fourier transform of A star H is H bar, or all the elements where if you play A star to it, you can still get something that sits in L1. Okay, so that's the basic framework. Now the continuous time random walk ansatz is to ask, what if after each tumble the sailor sits down and drinks for a random amount of time? Okay, so then the question is, what is the time of the M-blast first tumble? Okay, and again, if the time that he or she sits down, if those are independent, now the time of the M-blast first tumble is given by n times your delta t, which is the time that he takes to stumble around, plus the W1, Wn, the times they sit around. So now again, if we can take delta t to 0, now the number of n turns now into a so-called surrogate time, where we then get that number of jumps by time. Yes, by time s is given by s plus w of s. Okay, and so now we can take the Laplace transform of that and see that this is now, again, here's the Levy measure that we have for the waiting times to be infinitely divisible. And since we expect waiting times to be positive in this case, we only have psi such that this thing here is always going to be finite. Okay, but what we really need, of course, is the surrogate time by time t. So the number of jumps by time t, not the time of the nth jump. I think I misspoke earlier. And so t sub s is the time of the s jump. Okay. And now I can do a little bit of math, and I'll do it in a second. That will give you then a Laplace transform of the expectation of e to the minus qst of s sub t, that's given by this formula here. So how does this formula come about? So if you let little u be the density of s sub t and little r be the density of t sub s, and u and r the respective cumulative density cumulative distribution functions. Okay, so the antiderivative with respect to the dot for each of them. Then you just take the Laplace transform of e to the minus qst, which of course by definition is this integral here. And now you take the antiderivative with respect to s. So a little q comes to the outside. And now you use that the CDF of ut is the same as 1 minus the CDF of rs. And so ut is the same as 1 minus rs CDS. And now if you take the Laplace transform with respect to t, then you get that you get here 1 over lambda, because e to the minus qs of the 1, that's just giving you 1 over q times q is 1. The Laplace transform of 1 is 1 over lambda. And you have here the rest. Now you know that the Laplace transform of RST is given by the lambda plus omega head of lambda, and e to the minus s lambda plus omega head of lambda. And then, since this is now fixed in s, it goes in the denominator, and you get your result. Okay, so long story short, okay, we end up with this formula right here. And so now we can replace the e to the minus qst with e to the s sub t a star. Okay, so we can use a functional calculus, or we can use basically just, we are interested in the evolution of our semigroup, but now subordinated to s sub t. So s sub t is now the surrogate time by time t. And so this is going to be our solution, our distribution of the original spatial process subordinated by s sub t. Yeah, and so here is our formula for the Laplace transform of the semigroup that is giving us the evolution of the probability density if you start with probability density mu. Okay, it's fine. We have a Laplace transform solution. What we really want, though, is some form of differential equation that we then can later on move away from the probabilistic theory and go to a physical theory, doing being able to interpret the terms and then add or subtract forcing terms and make things nonlinear, make things time non-homogeneous, where keeping it in the probabilistic realm would make things very, very cumbersome, because you don't have necessarily probability distributions, don't have necessarily positivity, whatever else anymore. Okay. All right, so if we have our little formula here, and in blue, your head of lambda, the Laplace transform of u is given by this formula here. Well, we can multiply both sides by lambda plus omega head of lambda minus a, and bring it to the outside, and we end up with this equation right here. Or if you now invert it from the Laplace transform, we end up with this Caputo type differential equation, where if omega hat comes from a power law, you would get a fractional Caputo type derivative on the left hand side, but you still have your d over dt there as well. Okay, that's one thing you can do. You could also take your equation up here and or take this fraction and divide top and bottom by lambda plus omega head of lambda. And you end up with this equation. Okay, or you get an equation where d over dt u of t is a star applied to the convolution of k with u, where k is a Mittag-Leffler type function. It's actually quite a nice function. Or you can get a Volterra integral equation. If you still just multiply, divide by lambda on both sides from what we had right here, you end up with this equation, which then in the end looks like this. Yeah, so we have three equivalent equations, okay, that all have the same solution. The question or the art is to say which of those equations is the one that is going to help me the most to now generalize my equation and modify my equation, where I understand the terms, where I can model it so that it makes sense to the scientists and they can play and use them successfully. Okay. Now, for the third one, I really want to mention the monograph of Jan Brüss in 1993. He has, it's a fantastic monograph. He has really solved all the existence, uniqueness, and all kinds of results are all in there. Unfortunately, it is a pretty hard read, and I think that is one of the reasons that his work isn't really known that much in amongst our group. But if you understand semigroups and if you understand Laplace transforms, give it a go. It took me probably about 5 to 10 years to finally get into it. But in the end, if you're solving this equation or working on these equations or working on that equation, if you have an existence result here, you will have an existence result here and vice versa. All right. So before I say which one of those is my favorite equation, okay, I want to note that from the get-go, we actually have a clear decomposition of our probability density. We clearly decompose into a population that is stumbling around and a population that is sitting and drinking. Yeah, so we have a mobile and an immobile population. Okay. And we can actually get the immobile population, the density of the immobile, or the relative density of the immobile population, by looking at the Levy measure of the waiting time process, which is giving us the survival function in CDRW theory. And so I am in the immobile population if I was mobile as time units ago, and I survived sitting down for at least S time units. And then I integrate over all possible S that I can have so far. And this will go and give me my immobile density, or at least a distribution. Okay. So taking Laplace transforms, it's a convolution, so it's just a multiplication. So the psi, that is our omega head of lambda over lambda, psi of the tail, and multiplied by the Laplace transform of u hat mobile. And so now since u mobile plus u immobile is u, you get that u hat is given by 1 plus omega head of lambda over lambda, or if you bring it on the same denominator, you get lambda plus omega lambda over lambda, which was exactly this term right here. Okay. Or which was our k, at least it's the inverse of k. And so we get that u mobile is indeed k star u, and so we get an equation that just says u prime is equal to a star applied to u mobile. Okay, which should make a lot of sense. Now the rate of change of my concentration u at any point x in time is given by the operator a star moving around the mobile particles. The immobile ones, well, they just sit there, they're immobile, they're not moving. So they should not take any part in what the operator a star sees and how it's moving, how it's affecting the rate of change. Okay. So now let's get physical. So let's try to start away from moving the probabilistic ansatz and say, okay, let's really talk about rate of change, or let's see whether we can expand our model and make things, say, non-autonomous. So what does this equation model? Yeah, so without the red t's, without the f of t, that was just the equation we had earlier. That models our drunken sailor sitting down and intermittently. Okay, but now that a star depends on t, now that f, we have some forcing maybe, but I don't think it is quite clear. It's certainly not obvious what f is or what it should be or what it signifies. Okay. What about this one? Well, it is basically a local. The first equation is more or less local in time. I have u, I have some um that depends on t. The whole equation only depends on t. Of course, they are linked through here. That it's not that you have here a time dependence or a convolution, a time convolution in here. But in this equation here, it is acting locally in time. A star at time t acts on what u mobile at time t is. So if I change my operator that is moving my particles around through changing boundary conditions or through changing field strengths or through changing velocity or whatever else, through changing dispersivity, if that change depends on time or depends on whatever, that's how it should be done. Similar, now f is clearly a forcing function. A positive f increases the rate of u, a negative f, it decreases the rate of change of u. Okay. And the Volterra integral equation, well, I mean, it's just the antiderivative of this, except that the a wouldn't sit here, sits on the outside. So again, the time dependence here is probably not quite clear of what it is. One can probably come up with a way of doing it. This f of t is a cumulative change. This is the antiderivative of this one here. But certainly it's easier to identify terms in the second differential equation of what the physical meaning is or should be. So let's take a little bit closer look, and let's address this little delta t that I kept around. So that it is the derivative plus omega hat, the Caputo derivative, not just the Caputo derivative. Could we scale this away? Well, I'm claiming that if we throw away this first derivative, then what we're losing is this decomposition. So we can either say, well, we get the immobile concentration by using the survival probability argument. Then I get this relationship between u mobile and u immobile here. Or I can say I certainly only want the derivative of u to be, or a only be acting on mobile particles. But if that's the case, then I get suddenly negative concentration and the things will fall apart. So while this thing here does make sense, A is then not just acting on the mobile population, which then really makes this immobile decomposition suddenly different, and you're not modeling an intermittent process, you're modeling something else. It might be approximately similar, but certainly something that one might have to think about in a little bit more detail of what you're actually modeling. Okay, so if you were sitting at tables, I would like you to give a little task and give me an equation, whose solution models particles, that move intermittently, say with velocity 1 to the right. So we stay in one dimension and have a waiting time alpha stable process, alpha between 0 and 1, and we decay exponentially at rate c. So that we die out like a radioactive particle, and everything then just disappears at an exponential rate. Okay, what would be the differential equation? Well, if you think something along those lines, you're in good company. So that is something that where we take the minus partial with respect to x. So this would be the velocity 1 going to the right. We have our initial concentration. We have our forcing function that is now dependent on u. And we take here a 0.75 stable waiting time process. And that would give our k hat. Okay, so this is something that back in 2006, when we did a workshop in New Zealand, a PhD student presented, Trevor Langlands, and let me show you the movie that corresponds to his result. 1 second, here we go. All right, so the yellow is the total concentration, and I also plot the mobile and immobile concentration. Here we go. Beautiful lines, beautiful snakes, but certainly something that is slightly unexpected. I certainly was jumping up and down at that conference, at that workshop, and saying, this can't be, this can definitely not be. How can you possibly get negative concentration if your model says, we are just reducing our population exponentially. We die out, radioactive decay, and we are moving around. Something is going terribly wrong. Okay. So what is it? So the movie is correct. Yeah, I have to say the movie is correct, and actually it turns out that this was the best thing that could ever happen to this poor PhD student, because now suddenly you really have a paper and have several papers explaining why is happening what is happening. Okay, and the reason is that your survival function is not correct anymore, right? So not only, your survival function also needs to be exponentially tempered, otherwise you bring back people from the dead. The concentration that you're drawing in here is not, your u is not taking into account that you had radioactive decay. Okay, so student was a student of Henry in Sydney, and so they got a couple of papers out of there, and then from there on, there's a whole range of papers on with Angstman and Jin and others, but also Sergei Fedotov here in Manchester has a couple of papers and a book, I think in 2010, that deals with that quite in detail. Yeah. So my survival function has to be multiplied by e to the minus ct for this to be correct. I'm not coming back. I'm not going back into, my immobile concentration is not just what happened as time units ago times my survival probability, but also I'm decaying exponentially. So I still have to be multiplied by e to the minus ct. And if I take that into account, now I can do a little bit of algebra, and I get that actually my mobile concentration is given by e to the minus ctk star u. Okay, and if I do that, then my evolution looks like that. Well, the blue line is the mobile concentration, the red line is the immobile concentration, and my total mass is decaying exponentially at rate e to the minus 1/2 t, and everything looks like as it should. Okay. Probably a good time to point out that the solution here is compactly supported. That contrary to the case where you do not have the first derivative as part of your governing equation, here the first derivative ensures that I cannot have, I have to take a minimum amount of time delta t in order to make a jump. So I cannot have a situation where my delta t gets so small compared to the jump size that I suddenly move out to plus infinity. Yeah, so the dOdt actually keeps my subordinator compactly supported. Okay, so it does make a difference whether old agents are removed or negatively charged agents are added. Okay, so that is basically my take-home message from the equation that we had earlier. If I look at this equation right here, basically what I'm doing is I'm adding negatively charged new particles u. Okay, and since I have aging in my process, this k hat is not a Markov process. The new negatively charged particles move faster, are still more eager to move than the old ones that have found a trap and sit in there for a long time. And so what happens is that this concentration of negatively fast particles will take over the positive ones. And so if you add the positive and negative ones, you end up with a negative concentration. So that's really what we saw in the movie, is adding negatively charged particles and looking at the net between positive and negatively charged particles. Where the negative particles, again, were fresh particles. So they get to move around for a while before they fall into the traps, before they sit for a long time and have their drink. Okay, so putting it all together, we have our rate of change for u is given by the mobile particles being moved around, plus some forcing function, minus some depth function times u, plus some burst functions times u, and my initial condition. Where if I kill particles, I also have to kill their history. Whereas for the birth, I usually would only birth new particles. But if I want to birth things into immobile particles, then this can be done as well. We might see some of that in a second. Okay. Now, once you are in the non-autonomous case, that means that your parameters, that your operators can not only depend on t, they can also depend on other things that vary with time. You can now make them depend on other variables or on feedback variables, and so you end up with now a potentially nonlinear equation where your A star could depend on your mobile, your immobile, or the sum of them, your functions, your death rate, your birth rate, and so on. Whether you can solve them or what the probabilities of solutions are, that is another question. But before you want to answer those, you want to make sure that you are actually solving or working on equations that are physically relevant, where you understand the meaning of the equation. So far the focus was on u. Now, if we just replace u with u mobile plus u immobile and just write everything in terms of mobile and immobile, we get this equation right here. Okay. Now, I can replace this u immobile here again with just this expression, and I end up with a single equation that has just u mobile in it. That is an equation that I can solve by time stepping. and then I just get my immobile by applying this to umobile. Okay, so time stepping is indeed possible. Okay. Now, the next thing that we can potentially do is say, well, what if we actually go into not just a decomposition into mobile and immobile, but what if we go into a really two-agent system where if you are in umobile or U1, you move around according to one operator, and if you are in immobile or U2, you move around according to some other operator, A2. So you flip between two regimes, whereas you stay in one regime just for time delta t, and in the other regime according to our waiting time process. Okay. So for this to work, we need to keep track of particle location and age. And so for that, we now look at an auxiliary variable, let's call it h sub s, okay, that turned immobile at time s, and they are still immobile. Okay, or immobile is now, of course, meaning in regime 2. Okay, so how does HS evolve? Well, it evolves according to A2, but then also if we have a death rate, that would be something that then it gets removed with minus d of t h of s. Okay, but h sub s is such that it is the population of the mobile at time s. Okay. So h sub s at time s is the probability density of your mobile at s, and so those are all the ones that became moved then into our immobile or 2-bit, and then from there they evolve. Okay, so our total immobile concentration is now the aggregation of anything that moved into the immobile phase at times s and evolved there up to time t and hasn't left that phase yet, and so it still needs to get multiplied by psi of t minus s. Okay, so let's maybe do a little sanity check. Let's do a simple example. Let's say we take A1 the right shift, A2 the left shift, and we just take a nice exponential waiting time process. Okay, so actually something that is Markovian. Okay, so if I now look at the derivative of U1 plus the derivative of U2, that is now just A1 U1 plus A2 U2. Okay, so what does it model? Yeah, we move for time delta t to the right, and then we move for time delta, well, it's not quite delta t, but it's delta t times something that is distributed around 1, has average 1 e to the minus t, mean 1. So also delta t to the left. If I take delta t to 0, this is exactly what I get. So we move to the right, then to the left. What do you end up with? Okay, well, we can just go through the machinery. Okay, so U2 is 0 to t, and now we have here the tail of the Levy measure, so that's e to the minus, now the convolution t minus s, and then hs of t ds. Okay, we have here our differential equation for h sub s. We don't have any reaction, so that's just A2HS, and that's the initial condition at time s. And so this has a solution. So A2 is the left shift, meaning that is just that HS has to have this formula right here. Okay, and so now U2 is given by the tail of the Levy measure times our HST, which is that. Okay. Now we take the derivative with respect to time of U2. Okay, and the e to the minus t can go to the outside. So product rule is giving you a minus u2, and then the e to the minus s with the t in here, you will get a derivative, you get a u1 plus a get a u1 plus an a2 u2. So the u1 is the initial condition, and the a2 is what we have on the outside. Okay, now we take this equation and plug it into 1. So we get u prime is equal to minus u1 plus u2 plus a1 u1. The a2 u2 cancels out. Okay, now once you have this equation, okay, now let u to be u1 plus u2, and then do a little bit of algebra, and what you end up with is, lo and behold, the telegraphus equation, which is exactly what I hope you figured out what it should be from the beginning. So that's what you get if you move things around and you stay delta t going one way or the other. All right, so this all makes sense. It looks solid, so we can go ahead and start playing with some examples. Okay, so here's an example coming from it's a made-up example, but basically from hydrology, where we have particles going down a stream. The hyporeic zone is the bed underneath it, so the velocity is many magnitudes smaller in there than in the main stream. So we really still have a mobile immobile decomposition. So we say we go with velocity, we have a little bit of diffusion on there. Okay, we don't really move in the in the floor, and let's say we have a fractional time derivative, or a Levy, a fractional Levy waiting time. Okay, and now we're saying let's say we have a death rate of 5 if t is even, otherwise it's 0. So we are killing in the immobile particles if you are between 2 and 3, and otherwise we don't. Okay, so that gives me this movie right here. So we have an initial condition, mobile, immobile. So the green is the concentration in the riverbed, and the blue is the concentration in the water. Okay, and so right now it's daylight, so the green decays exponentially, and now at night it can recover, getting particles from the riverbed into it. Now it's again daytime, and we are decaying exponentially, being taken up by the plants, and recover, and so forth. Okay. Another thing we can do is now that we can work with systems, where things become closer to being nonlinear, where we take concentration, where we have 2 concentrations, one of resazurin, the other one as resarufin. Okay, one is fluorescent, easily measurable, the other not so much. Okay, and they interact. So again, in the river, the resazurin doesn't really degrade. The resarufin degrades, but pretty slowly. But if it sits in the ground, then the resazurin decays a fair bit, and resarufin decays a lot. Okay, and then we also have some that resolution turns into resolution at a certain rate. Okay, and the hope is, or the hope was, that we might be able to use that and measure the resolution to see whether we can from there determine what our parameters should be for our model. So this should give us hopefully a nice way of seeing how long do things stay in the bed, how long do they come out, and how fast do they come out, and with that maybe find a way to estimate those parameters in a nice and easy way. But so far we haven't quite succeeded in that. So the math behind it, I just want to flash it to show how smart I am, but don't expect it to really get much out of that. But again, I'd rather show you the movie. Okay, so no, that's the wrong one. No, this would be exactly so resolution and derive. And now for different parameters, you can get different curves and hopefully match those curves, and also in terms of breakthrough curves. And with that, the hope is that we can estimate the parameters. But so far, not much has come out of it. Okay. How am I doing time-wise? All right. So what about noise? Okay. So there, we actually have done a fair bit of work. If now in the end, if you have noise, you probably want to go towards the Volterra integral equation. Things become a little bit easier because taking derivatives of noise is something some people frown upon. But here you would get this Volterra integral equation. Then you talk about mild solutions by fixed points, and we can show that this thing here will have a solution that is in this path space if you satisfy a bunch of assumptions that you need that are reasonably general, and particularly if we have our first derivative in there, then things become quite nicely, and you can play off regularity of path solutions, regularity solutions, and so on to get nice estimates depending on the noise on how it's sorted. And with that, one last little note on numerics. I showed you some movies. It actually works reasonably well. The whole system of abstract Volterra integral equation, they do not depend on t, but the main tool that we use is Lewis convolution quadrature that approximated in convolution if the Laplace transform is known, and with that you can get reasonably fast algorithms. And code works reasonably well if it's c dependent and approximate noise. Of course, since you have to take account of the whole history, you're always going to have memory issues if you are doing a fixed time step, and which is something you have a hard time getting away from if you have forcing functions that really depend on t. And with that, come to the end of my talk, and thanks for listening.
Thank you very much. And let us upload. Thank you very much for a very nice talk. So are there any questions, please? Just please unmute yourself and ask. This is the simplest way.
Can I ask a question, Vasily?
Yes, please.
What is the reference for the last paper you mentioned about stochastic case?
Yeah, that is a little sore spot. We haven't published it yet. So we had the result of this thing here is, I guess, 5-6 years old. But I'm happy to talk you through it. But it's one of those things when your postdocs come to the end and leave and don't finish the work, and we haven't quite managed to get it out. And we have a big big paper on well, hopefully coming out eventually, but I'm happy to walk you through some of it. If you have a question, I'll send you a few things.
No, you can send me if you can.
Yeah,
And we will
yeah.
have it.
Good.
Thank you very much.
Okay, any other questions? Maybe I will ask them, Boris. There are some
Really?
new words which I never heard. Who are these guys? This Reza Zuzin, Reza Fufin? Are they people? Are they animals? Are they plants? What are this? What's the meaning of these things?
Say this again. Sorry, I didn't quite catch this.
These words which you are using, Reza Zufin, Reza
Oh, yes,
Fufin. Who are they?
Oh, that
Animals,
is
people?
no. These are chemical compounds.
Oh,
So yeah, so the resazurin, that is a mildly fluorescent chemical, and resaruvin is a very fluorescent chemical. So you put it in the water, and then you can just see how much resaruvin is in there by just seeing how much light is coming out.
okay.
Yeah.
Okay.
And so you have this chemical that so it doesn't degrade in the channel, but it's what they call a smart tracer. It notices whether it's turbulent or not, and if it sits, then it degrades. And if it moves around, then it doesn't really degrade. It gets enough oxygen or something like that. I don't understand the chemistry exactly of what it is, but
Okay. Thank you.
yeah. So you have this nice system of things moving and reacting and it being mobile or reacting being immobile, and you can then really play with the model and
Yeah, and you can observe it really. Yeah. Okay.
and you can observe it exactly.
Okay. Maybe some question from the auditorium who are sitting in room 2. No. No more questions. Okay, then. Thanks, Professor Baeumer again.
Thanks,
And
Vasily.
next, our talk is at 2 p.m. I suppose Professor Meshura will speak and Laura will chair, and then we have another session at 5 p.m. 15 today. So therefore, bye-bye for now, everybody. Thanks for your attention.